Hi everybody, today we are going to talk about inverse functions. So first let's discuss what exactly are inverse functions. So inverse functions, you can think of them as two functions that undo each other. So if there's any operations being performed, such as multiplication, addition, subtraction, even an exponent or a radical, they would eliminate all of those other operations. Another way to think about inverse functions is by knowing that with the two functions, the x and the y values of each coordinate are simply switched. So if you have a point that is at 2, 1, your inverse will have a point that is at 1, 2. And then lastly, it's good to know that inverse functions are a reflection over the line y equals x, which you'll see as we try graphing some of these. Okay, so let's talk about what I meant when I said functions that undo each other. So these two functions are inverses, and we'll talk about how to figure that out later. But to prove that they're inverses, let's show that they undo each other. So let's imagine that we take g of x, this function, and we substitute it into f of x, and look what happens. So we get... So I'm going to take out the x and I'm going to substitute g of x, which is this. Well, these will cancel out, and what I have is x minus 3 plus 3, which is just x. So it is essentially undid any operation that was happening. Now let's try it the other way. Let's imagine we take f of x and plug it into g of x. So instead of x, I'm going to substitute f of x. And I see the same result. I get 2x over 2, so g of x just equals x. So by substituting the inverse function, it essentially undoes any operation that is occurring in either function. Alrighty, let's talk about what I meant when I said that the x and y values are switched. So here is a linear function, and I marked off a few of the coordinates. So if I have a coordinate at 4, 3, that means I will have a coordinate at 3, 4 for the inverse. And if I have a coordinate at 2, 2, I will have a coordinate at 2, 2 for the inverse. If I have a coordinate at 0, 1, I will have one at 1, 0. If I have one at negative 2, 0, I'll have one at 0, negative 2. And if I have a coordinate at negative 4, negative 1, I'll have one at negative 1, negative 4. On the other side. There you go. Now, the third point I mentioned was that inverses are a reflection over the line y equals x. So the line y equals x is just a linear function with a slope of 1 and a y-intercept of 0. So you can see that if I actually folded my graph on that line y equals x, my inverse functions would match up because they reflect over that line. Okay, now that we know what an inverse is and what they look like, let's talk about how can you find them algebraically. And it's really easy to do. The first step is to switch where x and y are in your equation. You do not change anything else. You literally just swap x and y. Then you solve for y, and then you have your inverse function, so you rename it g of x, or whatever we ask you to name your inverse function. Alright, let's give it a try. We're going to find the inverse and then graph both. So the first thing I'm going to do is switch my x and my y values. So instead of saying y equals 3x minus 1, I'm going to say x equals 3y minus 1. Now I need to solve for y. So I'll start by adding 1 to both sides. And then I'll divide the entire equation by 3. And what I get is y equals 1/3 x plus 1/3. And since this is my inverse, I will call it g of x. All right, let's graph them to see if they work out. So my original function looks like this, has a y-intercept at 3, or at -1 and a slope of 3. And then my second function has a y-intercept at 1/3 and has a slope of 1/3. So it looks something like this. Now, if you trace the line y equals x, you will see that these, in fact, do reflect over the line y equals x. So we know that they are, in fact, inverses. Alrighty, at this point I'm going to ask you to pause the video and give this problem a try. Okay, thank you for giving this problem a try. This is kind of a strange case where when you switch x and y and solve for y, you end up with the same function. So the inverse function of f of x is essentially itself. And you can see that in the graph. Since it does have a slope that is perpendicular to the line y equals x, it is a perfect reflection. Alrighty, I'm going to have you try this one as your last example. Okay, thank you for giving this problem a try. So here, I switched x and y, and I solve for y. And remember, when you're multiplying by 3 in this step, you need to multiply the entire right side of your equation, so you get 3x plus 6. I graphed both of them, and I see that it does make a perfect reflection over the line y equals x. Alrighty, so that is all for today. Just remember there's many different aspects that you know about inverse functions, so you can use any of those to help you find the inverse.